Um, Now, in a build up to what we call fundamental groups and homology groups, which we hope to reach, inshallah, we are going to do some review on our back representations of simplices. Now, I told you we can represent simplices as vertices in vector space using what we call convex hulls. Now we saw that these vertices produce vectors which are linearly independent, and such that each vector can be written as a linear combination of other vectors in the plane. I gave example of two-dimensional plane. Now we are going to look at what we call standard form of representation of these simplices in n dimension. We are going to begin from one dimension. So I will call this standard form. Now consider a point in D node, that means zero simplices, okay? This is actually a one-dimensional vector space. So you have a line which is called, suppose this is your origin, and you have a unit length, you call E, or that unit vector, okay, representing a point. This is presented by x1, suppose this is x, x1 is equal to. So this vector characterized by this point in the one-dimensional Euclidean plane is actually represented by the equation x1 equals 1. Is it clear? That's a standard form where E is now a unit vector. Now what happens if you are in two dimension? In two dimension you will have two vectors. Let me call them E1. And you have another one here. Let me call it E2. Okay. What is the characterization of this point? This point is 1, 0. The point here in a unit vector along x-axis is characterized by 1, 0. And the point here along the y-axis is characterized by 0, 1. So the equation of this line is therefore x1 plus x2 equals 1. That's the standard form of representing simplices. And this is what now? This D1 is the past simplicity. This D naught. Normally it's not D, it's delta. Very clear? Now in D2, you talk of three-dimensional place. So you have vectors like this, unit vectors again. Okay, let me say this is suppose this is my E1, this is my E2, and this is my what? E3. Okay, or if you like, you can also say this is your E1, this is your E2, this is your, if you use the wrong representation, X, Y, Z. Exactly. Now a point in E1, a unit vector in E1 is characterized by what? 1, 0, E2, 0, 1, 0, E3, 0, 0, okay? And the equation of this is going to, now, what is the convex hull? If you want convex, so you join this, so you end up with what? Okay, a convex hull, which is a triangle, isn't it? A triangle, so the equation is x1 plus x equals 1, okay? These are convex hulls that lie in hyperplane, okay? This is called hyperplane, okay? What of D2? For D2 you have 1, 2, maybe 3, 4. Is it clear? So you have, we call this E1. It doesn't matter how you name them. E2 is, if you say this is what? E3, this is your E4. So E1 is what? 1, 0, 0, 0. What of E2? 0, 1, 0, 0. What of E3? 0, 0, 1, 0. What of E4? 0, 0. Now, let's see. If we join this, okay, you get what you call, this is triangle. This will be tetrahedron. The clear? The convex hull that you are going to create is going to be a tetrahedron, okay? So, and the equation of this is x1 plus x2 plus x3 plus x4 equals 1, okay? This is called standard representation for these simplices, okay? Yes. Actually, and this goes on and on up to, you can represent this up to dn, okay? Delta n, the simplex, okay? You can use what you call standard form. By using just unit vectors, you are going to create these simplices. And this is the past topic, I think, which is actually a rider to the one we discussed, like I said, using linear combination of actually line vectors. Now, we are now going to go to see the orientation of these simplices. Orientation. Now, how do you orient these simplices? There are two ways, like I said, of orienting the simplices. You either go clockwise or anti-clockwise, okay? Now, let me give example. Consider D2, okay, delta 2, that's the triangle. Okay. Triangle as a simplex, okay?